Hi guys. My name is Souryajit Roy. I'm from TFR CAM. Uh, this work with this work is joint work with Professor Jim Thomas, and we'll discuss some neural network models for the acoustic wave scattering problem. First I will start with a brief intuitive description of the problem. So what is this acoustic wave scattering? So you have a initial plane wave. So what do I mean by a plane wave? So you have say a single Fourier mode at some uh, place k naught. So you have e to the power I k naught x, and obviously because you take real things, you have a conjugate place where it will be there. So that will correspond to a single mode wave, and this wave is going to interact with a turbulent vorticity field, and the field is going to, the initial plane wave field will scatter. So what do I mean by scattering? So imagine a turbulent vorticity field as a flow field with a lot of modes, a lot of Fourier modes. So the initial Fourier mode is going to, as it evolves in time, the system is going to interact with this modes from the vorticity field, and it will create some neighboring modes. So if initially it was in a disk of say radius r, in some small neighborhood of the disk of radius r, new modes will be created, forming a ring-like structure. So this yellow part shows the intensity of the new modes. The dark part is basically nothing is there. So the major reason this ring, I will go to the exact mathematical detail, but I will give an intuition why the ring-like structure is forming. So these are the equations which are governing this scattering dynamics, scattering problem. So you have the acoustic wave velocity and pressure. By the way, these are all pressure field plots. So acoustic wave velocity and pressure, and this is the linear part of the equation, and this is this interaction term, which is basically how the acoustic wave is interacting with the turbulent vortex. So u bar and v bar is from the vorticity field. So imagine this term is not there. In that case, if you focus on a wave field of the form e to the power I kx minus omega t, and suppose you focus on a single frequency, from the dispersion relation you will find the new modes which will be there forms k square is equal to k naught square. So initially if you stay on this disk of circle of radius k naught, you will still stay there, but because of this term, a certain ring will form where the thickness of the ring is basically governed by this epsilon, because the modes interact and new modes are formed. You can explain this more accurately with like writing the equations, but yeah, I'll stop there. So this is the intuition why a ring is being formed. So epsilon is basically this wave vortex interaction strength. So this is our problem, a plane field, it's going to scatter because of interaction with a vortex. So what are we going to do with this problem? So we are looking at this problem, and we want, if we are solving this problem with a traditional numerical solver, you have certain restrictions where your dt will depend on your spatial resolution n, and higher resolutions will require smaller dt. And so that will make the better resolution simulations you want, you have to reduce the dt, and that will create more computational complexity. So we want solvers which preserves the spatial resolution n, but we can integrate faster, as in we can take larger time step tau, which is much bigger than dt, and go directly to there instead of going through the intermediate steps. That is how we are making it computationally faster. So basically I explained it. The goal is to develop a neural network based surrogate PDE model which reproduces the scattering dynamics accurately, and it does it faster. And as for specifics in our problem, we did a numerical simulation with resolution 768, dt 0.01, but the operator framework I will propose will integrate preserving a certain level of accuracy with steps of tau equal to 1. Yeah. So in this, what is the data set we are working with? The data set we are working with, as I explained, you have different initializations of k0 on a disk of radius r, and that gives you the initial UVP, where U and V is basically from the gradients of P. This is because if you look at the linear part, U and V are the gradients of P. So now you have certain number of modes on the disk of radius r. In our case, I have taken r equal to 6, and different initial modes will give to different initializations and have different simulations and different solution trajectories. And also you need u bar v bar, which comes from this by solving the 2D vorticity equation till a certain n time. So you solve with different random initialization till a certain time. As time progresses, larger and larger structures are getting formed. So we have different, I have generated 2D vorticity fields with different n times. So this 30 and 60 I am going to keep for training, and the rest of the things I will keep for testing. So generalization purpose, we want to see that the neural network model we finally design is going to generalize over unseen vortices and unseen initializations. For initializations, I trained with 20 different initializations, positions of k0 on the disk of radius 6, and 20 totally unknown random initializations I kept separate for testing. So, and epsilon 0.1 was always fixed. I didn't change that. So so I will show you two models. One is a artificial neural net, ANN based model, and the other one is the main model, which is the framework I proposed, which is a neural operator based model. So what is the difference between these two models? So basically the ANN requires for training the solution snapshots and also the partial derivatives of the solution snapshots, which is essentially the right hand side of the equation, and a certain structure of the PD for learning, which makes it basically a regression problem. I will explain you why. So it requires a lot of information, the structure of the PD. On the other hand, the neural operator based model doesn't require anything except the solution trajectories. It doesn't know anything about the structure of the PD. So this model I am basically keeping as a neural net baseline to compare the neural operator model with, because with this much information, it's expected this model is going to be very accurate, because function learning is much easier than learning an operator. So what is this, the baseline ANN model doing? It's taking inputs UVP, U bar, V bar and their derivatives and predicting the RHS term. So you can see which is the UVPT, so partial derivatives of UVP. You see in the input I am basically enforcing a certain structure of the PD. This is a knowledge of the PD in a certain way that these derivatives are there. So it is passed through a artificial neural net with 3 hidden layers, 64 neurons each, and it gives you the output, and that gives you a certain PD, which is del by del t UVP, a neural net of this input UVP. So what is the advantage of this method? I already explained. It makes it a function regression problem, which makes it easier to solve, and the universal approximation capacity ensures that there exists ANN which will approximate it, but again the convergence and guarantee it will converge, those are kind of trial and error and a black box thing. And so what is this ANN model trained on? I explained what we are training on, but the one thing I didn't say, we are training with snapshots till time t equal to 40 at certain intervals of 5. But double the time I will time integrate to see it goes beyond the time till which we trained. Okay. So and by the way, what is artificial neural net? Think it is as a combinations of linear operations and nonlinear activations, and finally you get the output. In this case, you have 3 linear layers combined with ReLU nonlinear activations. Okay, so now this is the main framework, which is the operator framework, and the more complicated one. So I won't go into all the mathematical details, but I will give you an intuition for this, what is happening. So, so this is basically Fourier neural operator falls into the class of integral neural operators. What does it do basically? So it learns the solution operator as a, like if you write the solution as xt plus tau is equal to xt plus a certain integral operator, it learns this integral operator. So it from t to t plus tau is an operator which is it learning the solution map. So what is x here? In our case, it is UVP. So now this whole there is a theorem which guarantees, again, the universal approximation theorem for Fourier neural operator, which guarantees such there exists a framework which will approximate it, and the Fourier neural operator is basically designed on writing this, approximating this integral thing with a kernel, where kernel is the thing where the neural net is going to learn. And you write this, so it happens as a sequence of blocks. You have an input V, it moves to output V tilde, where each time V tilde is a nonlinear activation of a combination of a linear map on that and a kernel function on that, where this kernel is approximated. The main thing it is called Fourier neural operator is because the kernel is basically approximated in Fourier space, learned in Fourier space, because if you write the convolution in Fourier space, it becomes basically multiplication, and for certain Fourier modes, you learn the weights. So if you focus on a certain mode, you learn the corresponding weight, which gives you this kernel operation. And there is a finite set of modes which you are considering, which is basically again depends on the problem. And for our problem, I basically considered from a certain band of Fourier modes, which comes from how the vortex modes, intuition of how the vortex modes interact with the wave modes, and they should stay in that ring. Anyway, so basically what it takes a certain history of the solution, goes to the next state. So it has a certain length of history. In our case, it is the length is 5, and then it goes to a next step xt plus tau, so which is basically xt plus 1. In our case, tau is 1, and we do it for a certain number of steps, 10 steps, and we consider all such trajectories. So you have a true trajectory of length 10 and a predicted trajectory of length 10, and then you compare the L2 loss between them, and you consider all such trajectories in this time range. This is how you learn this autoregressive time stepping. And then again, in this case also, we are going to see how well it does till time t equal to 80, double the time. Okay. So now I will show some results. So this is a certain movie of how the solution progresses for an unseen initialization and an unseen vortex. So you can see this is for the ANN. This is supposed to do decently well. The error is 1 order less. You can see scattered structures now. And then you have a ring formation corresponding to the scattered structure, which basically corresponds to the scattered structure. And the error is here also 1 order less, very small. But if I go to the next FNO, so that was kind of a neural net baseline. You can see the error it's still doing decently well, but the error is slightly higher. That was 0.2, here it's going up to 0.6. And you can see darker yellow colors at the end, so it's slightly higher in the Fourier mode also. So this is just one certain case, and I have cumulative plots now, which will tell you that actually the FNO is coming close to the NN with bit lesser accuracy. So the ANN, if you look at all the average of correlation between the at different time points between the truth and prediction, physical structures. You can see the correlation stays above 99.8%.
Try to wrap up.
And for the FNO model, it is a slight below, it's around 98%. And similarly, the L2 error is really small, 0.05 relative L2 error. It's all average plots, average over all test cases. So, and here it's slightly higher. So the conclusion is mainly both models are generalizing to unseen vortices and initializations. Both models are time stepping beyond the training time horizon, with the error staying one order less but growing with time. The NN model is more accurate, obviously, because of the more information from the PD structure. The FNO model, although the main advantage of the FNO model are two things. It doesn't have to know the PD at all. It learns the PD operator just from the solution snapshots. And it also, the ANN gives you a certain PD model which you have to integrate, time integrate with the same DT and N as your numerical simulation, but which is 0.01, the FNO is going to just take 100 steps in one go, which is 1. So it is at least 100 times faster. I didn't write the exact time, but it will be much more faster. And future work is, I want the FNO model can be tuned for, I think, much more accuracy. It's ongoing work with the FNO model. And we should compare it with more operator architectures like DeepONet. And there are some traditional architectures which were previously used to faster time stepping like UNet, which should be compared with the FNO. And in tuning, a lot of things follows, right? You can you can try to do it faster and all with taking larger steps, but not sacrificing too much in accuracy. So yeah, all that is there. Yeah, that's all.
Let's thank Souryajit